There we go. I think we got all the buttons pushed. Okay, so thank you first for the invitation. I'm quite pleased to be here. I think this is my fourth presentation to an IAFI chapter. I'm collecting those like Scout merit badges or something that I sew on my sleeve. But over the years, I've just given different talks, often related to this topic, but that has really sort of come together into this article that Dale was talking about with Joel. And some new work that Joel and Sky Cooley, who's in Montana, and I have been working on. So this is a bit of a combination or a mix of lines of work that are at different stages of development, some more mature than others, but they're all really telling and pointing in the same direction. And so for us, what I'll talk about tonight, if the slide like to go forward, yes, there they are. We're going to really revisit some concepts that are 100 years old or close to 100 years old because they were really proposed by Bretts. They might not have been articulated exactly the same way that they are today, but fundamentally those ideas were Bretts's to start with. So in his early years in the Channel Scablands, we'll talk about Moses Coulee tonight, but Bretts really identified Moses Coulee as one of these really interesting, peculiar places. He recognized that there was scabland terrain in that area. But it's, as you'll see in a minute, it's always been a bit of an enigma. There are some open questions about Moses Coulee that have always been perplexing, and they've been perplexing for the last 100 years. But also, Bretts was immensely good. I got to let more people in as we go. He was immensely good at thinking, let's just, what we like to say today, thinking outside the box, but coming up with really clever alternatives and interpretations for some of the observations he was making, because he was fundamentally working in a very unusual landscape. He was working in a place where, as Vic Baker likes to say, if you work in the Channel Scablands, you have to throw the book away, the geomorphology book, because you can't really apply the principles that you've learned in sort of introductory classes. So your textbook on fluvial processes has to go out the window a little bit because the landscape is just fundamentally different. And so one of the questions that Bretts was working on and thinking about is the idea that there might be water and water generated underneath an ice sheet in southern British Columbia. And that's a theme that we'll revisit. Bretts had firmly sort of in his mind the idea that volcanoes erupt underneath the ice and that's a way of producing water. It's not the only way, but that was the level at which he's thinking, close to 100 years ago, imagining in a way the hydrology of an ice sheet that today we realize is actually pretty close to how it works. So I'm constantly reminded and amazed at how clever Bretts was in the way that he tackled some of these problems. So here are the key ideas that I'd love you to take away from this talk tonight. I'm going to show you two major lines of evidence for having multiple water sources that affect the Channel Scablands that are not tied to glacial Lake Missoula. They're from the same geographic, but they're really areas that are to the north of the common scabland floodrivers. Those two sort of parts of the story tonight is that some of those water sources are subglacial. They come out from underneath the ice, and some of them are proglacial. But they both occur and they both create records, landform and sedimentary records that are within the areas of the Channel Scablands and the floodrivers. And of course, if we can come to that realization, we then also need to think about how we might need to reinterpret our current understanding of that record of landforms and sediments that we currently associate and attribute to drains of Lake Missoula. So new water sources means probably a new framework or an expanded framework in terms of where the water comes from. So the areas we're talking about this evening, the Channel Scablands, you're probably familiar with this area to some degree, but for those that may not be fully, let me just see if I can get the laser pointer to work. There we go. The general Channel Scabland area, Spokane's over here on the right. This is the Cheney Palouse tract, the Telford Trap Creek tract, the Grand Coulee, the Moses Coulee, and Moses Coulee, with very importantly, we'll focus a lot in this area this evening, but this arcuate curved area here is called the Withrow Moraine. It's the terminus of Okanagan Lobe, the lobe of a lobe of this Cordilleran Ice Sheet around its southern extent that extended as far as that position. How many of you have been to Moses Coulee before? Wow, most of you. Okay, so I'm showing you pictures, but you've already got a mental picture of what that looks like. It's striking, obviously. It's an incredible landform or coulee in the Scablands. It's the second largest coulee after Grand Coulee. It deeply incised. It has all the morphological characteristics of a coulee we expect because of this flood basalt that produces or leads to having these very vertical walls and flat bottoms.
What is that noise?
That's quite diagnostic, and we see it with Moses Coulee. I mentioned the fact that stigma around Moses.
Over there, if it was louder, he kind of perked his ears up for it.
1 second. I'm gonna have to be like the mean teacher, but whoever's at home and hasn't muted their microphone, could you please do that?
Dr. Lesemann, would you like me to do that part of that?
I just need to be able to forward the slide, so
Yeah,
that's
yeah.
okay. Yeah, you go ahead.
I'll do the mouse and you do
Sounds
the
good.
keyboard.
So the enigma of Moses Coulee is really tied around the fact that it has very poor connectivity to skyline floodways, unlike all the others. So I'll go back on my map real quick, and you can see the difference. If you look at the Grand Coulee, there's no question that it connects to the Columbia River. Same with the Telford Craft Creek and the Cheney Peninsula. But when we look at Moses Coulee, sorry, what is peculiar is the fact that the coulee sort of rises towards past the Withrow Moraine onto what we call the Waterville Plateau and just ends there. Doesn't connect obviously to the Columbia River or any other flood route, and yet it's the second largest of all the coulees that we have in the Scablands, which would, by implication, require some fairly sizable flows of water to create this coulee. That question, that enigma, was identified decades and decades ago. Early explanations by Bretz and some decades later by Larry Hansen invoked the importance of probably glacial meltwater to the origin of Moses Coulee, but it was never fully articulated. And currently, there are some explanations to try to account for the fact that it's poorly connected and yet shows us lots of evidence of erosion. And those two models involve some form of diversion of water around the margin of Okanagan Lobe or overspilling through a valley called Foster Coulee. If we have time, we'll get into some of those details, but we'll see where we end up. So where we'll focus are these two areas. This is the work that Joel and I have been working on, and we recently wrote up and was published, and it's focused on the areas around Omak Plateau and the Waterville Plateau. The Withrow Moraine is this blue line, and that's the extent of the margin of the Okanagan Lobe. So Waterville and Omak Plateau were both covered by ice completely. And of course, since then, the lobe was retreated at the end of the last glacial period, but unlike other areas of the Channel Scablands, this area is covered in ice. Other areas are proglacial. They're always in front of the ice to some degree. When we look on Omak Plateau, as an example from that northern extent of the field area, what we see very strikingly is that there's scabland on those surfaces. It's pretty unmistakable. We happen to be at the feather edge of the Columbia River basalts. So some of this example of this channel is cut into basalt, and not too far below that surface is some crystalline metamorphic rocks of Okanagan Dome, but fundamentally it's a scabland landscape. Oh, pardon me. This is another example of a channel, also underneath Okanagan Lobe. It's on Waterville Plateau, but again, scabland. So one of the fascinating aspects here is that we're seeing evidence of landform, the scabland terrain, the boxy channels, much like we see everywhere else, cut into basalt, and yet we're in an area that's glaciated. So there's a similarity, and I would argue almost identical morphology to channels that are cut underneath the ice versus some that are cut in front of the ice, or produced in front of the ice in the traditional scabland area. On a regional scale, if we map all these channels, we end up with this configuration. So what we're seeing, when you're looking at here, is the Withrow Moraine is the white line. That's the extent of the Okanagan Lobe. And the examples of photos that I showed you were from Omak and Waterville, a couple field examples, but the regional pattern of mapping reveals this incredibly intricate, what we would call an anastomosed network of channels that cover the vast majority of both the Waterville and Omak Plateau. There are other landforms that come into play here. For example, the white ridges, which are recessional moraines, and the little yellow squiggles, which are eschers, and we'll explain in a minute how they fit into this picture. But fundamentally, there's a channel network that exists in the area covered by ice that has that configuration and really is a scabland network of channel. I want to take a second to mention the fact that this regional network of channels was partly mapped in the 70s by Larry Hansen, what he termed the Mansfield channels. It's a subset, or it's a portion, a small portion of the broader regional network that's now emerged. But Larry Hansen is really one of the first persons to start mapping this channel and sort of start building the thinking around the significance of these channels. He passed away shortly after his PhD. Much of his work was never published in an article or in a journal, but he's got a thesis that is absolutely fantastic and full of really thought-provoking ideas in terms of what that landscape might record. So we're building, just like everybody else, we're building on the work of Larry Hansen, and Brett's was building on the work of predecessors. So I just wanted to acknowledge that because that's a really important part of the work that happened on Waterville Plateau. So you may have seen this diagram before. This is a colorized version of something that Vic Baker produced many years ago. And it's the sequence of erosion for scablands. So this is your traditional, not the one that I was showing, the typical, the conventional scabland terrain that we have for the Cheney Palouse. And it starts this way. If you take it from the top, there's a lush blanket of variable age that covers the flood basalts of the region. And when we have a drainage from glacial Lake Missoula and we overwhelm the surface drainage system, this area gets completely swamped by this flood water, and incision through the lush cover begins, and enormously powerful turbulent structures in the flow start to, these are basically what we call caulks, which have this incredible lifting action due to the turbulence. We start to incise into the flood basalts, into the bedrock. The jointing helps this process, and we start producing the coulees that are now, the defining features of channel scabland. So we incise downward through lush, progressively through bedrock, and ultimately we produce, once the flood wanes, we're left with this configuration of boxy coulees. I'm going to propose a slightly modified version of this for what we observe on Waterville and Omak Plateau. Slight differences, we're going to replace the lush with till. So these brown areas are not windblown sediments, they're glacial sediments. They're the basal till of the Okanagan Lobe. And if you're on Omak Plateau, there's some amount of basalt and grade, just like in Baker's diagram. And then there's this pink rock beneath it, which is the crystalline or metamorphic rocks of Okanagan Dome. And we're going to erode, instead of eroding through lush, first we'll erode through till, then through the basalt, and to some degree, in some places, a little bit through some of the metamorphic rocks. The biggest difference is that our interpretation suggests that erosion actually happens underneath ice. So it's not happening in a subaerial setting where the water is simply overspilling onto this expansive landscape of lush. It's happening in a confined setting in the sense that the ice above what will eventually evolve to be the scabland terrain of Omak and Waterville Plateau, that flow is confined within a channel that is partly covered by ice. So we're arguing here instead for erosion, we would call subglacial erosion, so erosion underneath the ice, rather than proglacial overspilling of the Lake Missoula waters. So the question that immediately arises when we propose this is what makes this particular scabland terrain subglacial versus some other form, which would be a subaerial scabland terrain. We said that they're very similar. So if we see similarity of form, it's reasonable to expect similarity of process. And so we can recognize that the scabland terrain on Omak and Waterville might be formed by water, but what makes that water flow underneath the ice? What's the evidence for it? So I'm going to walk you through or take you through some of the steps that are the key landform relationships and observations that allow us to establish that erosion of the scabland happens subglacially rather than in front of the ice for traditional scabland terrain. And we're going to pretend that we've got a somewhat virgin surface without channels, but there could be pre-existing fluvial drainages or even channel systems from prior glaciation. But let's just play along and keep things simple. And you'll notice the first thing is that there's a divide, topographic divide, a high point that would, under non-glacial conditions, have a stream or stream flowing in one direction and stream flowing in the opposite direction. We put the Okanagan lobe on top of it, and we are going to have episodically, this is our proposal, drainage of water subglacially underneath the ice, and it's going to excavate coulees and scabland terrain underneath the ice. It'll produce for us basically this configuration. But one of the critical differences right at this stage is the fact that the flows from our starting point have breached through and eroded through a topographic divide. Regular streams can't do that. Regular scabland does not show you that relationship. Regular scabland tends to follow the topography. Subglacial scabland terrain is capable of breaching and eroding over topographic highs because the flow is fundamentally pressurized by the weight of the ice above it. So we're getting water to flow uphill in the most simple way of framing it. And we can do that, unlike regular streams can. We can do that because ice pressurizes the flow and drives the water against adverse or up over adverse gradients. So the example that I showed you in this photo a few minutes ago of scabland terrain from Waterville Plateau. This is our proposed subglacial scabland. The blue arrow shows you that exact channel here where the photo was taken, but there are many others. But importantly, that line, black to red, is the topographic divide. It's the high points, the regional high point, and the color reflects the elevation of that point. But what you'll notice is that the channels cut right across, not just this one, but so does this one, and all of the even smaller ones. They cut across or through and breach that topographic divide. That is a critical piece of evidence, and one that very strongly points to this idea that the flow is pressurized by ice. In other words, flow happens underneath the ice. The previous cartoon showed you an example of fairly high magnitude flows. We can also recognize that there are lower magnitude, perhaps more steadily released in terms of the production of water. And in glaciers, that water can flow inside conduits that are ice walled. You can think of them as a pipe at the ice bed interface, or a half circle, as we often like to represent it, which is pretty close to the right geometry. And that conduit inside the ice at the ice bed interface carries meltwater, but also carries sediment, so that when the flow wanes and the sediment is deposited, it produces a landform that we call an esker. So an esker is unequivocally a subglacial feature. It forms only when flow is confined to a conduit at the base of the glacier. And where we see eskers in the region is eskers oftentimes eskers on the floor of the channels, on the floor of the scabland terrain. So by superposition, it requires that the channel pre-exist the presence of the esker, and the esker being subglacial also creates a situation where the channel must be pre-existing and is also likely a subglacial content. So we're looking at relationships of landform that allow us to establish the setting. Some of the eskers do cross over the boundaries of these scabland channels and sometimes onto the flanks. It's telling us that when we produce these lower magnitude flows, the hydraulic potential is a little bit different. It's all okay or all consistent with how we understand ice sheet hydrology to function. And then if we move even further in time, at a time when the ice sheet is retreating, in the process of retreating, glaciers and ice sheet leave behind moraines, what we call recessional moraines. They're really produced by the seasonal or few-year fluctuations of the ice margin that push and bulldoze a little bit of sediment back and forth as the ice is in an overall pattern of decay and retreat. And what we're seeing is that these recessional moraines drape the channel margins, sometimes overlap some of the eskers, and they further reinforce this idea that the channel in which all these sediments and landforms lie must pre-exist all the landforms and sediment, and therefore are all produced subglacially. The last component beyond the recessional moraines is the fact that on a regional scale, this is very schematic just to show you the basic relationship, but on a regional scale, this entire network is organized in this anastomosing pattern, meaning that it's a system that doesn't follow or is not organized in the traditional way that we think of fluvial drainage system with these sort of tree-like structures with a very clear hierarchy. In this case, we're looking at channel networks that branch and reconnect and diverge and reconnect and produce this widespread coverage, essentially, of channels that are forever crisscrossing and bifurcated. That pattern is also one that we recognize in glaciated areas, and it's one that's very diagnostic. You see it in the scablands also, of landscapes where there's an excess amount of water to evacuate on a drainage system that is poorly adapted to remove that volume. So it's telling us a story of excess amounts of water that need to be evacuated and yet that can't fully be captured by an existing drainage and therefore is much more distributed. In the lingo of glacial geology, these types of channels with these types of landform relationships with eschers and intercessional moraines in that particular anastomose patterns are called tunnel channels. And that's what we have here. These are tunnel channels. If you'd like some analogs, I guess you can't see my title, but it says analog. So do we know of tunnel channels elsewhere? Absolutely. Every major ice sheet has some example of tunnel channels. This is an example from Scandinavia. And I'll just draw your attention right away. The channels themselves are the pink areas. You'll notice the anastomose pattern, identical to what we see on Waterville. There are eschers, the green lines that lie within the channels themselves. The areas between channels with the purple stripes, or the purple lines, these are drumlins. These are, think of them as till uplands that have not been fully dissected. So we see these in every major paleo ice sheet. They're really common. And we may, I'm not exactly sure where we are on this DEM, but you'll probably recognize it. We're probably standing in a net, well, we are standing in a network of tunnel channels. The Puget Sound is crisscrossed by an extensive network of exactly the same type of subglacial water channels. So if we're talking water and water discharge, and we're talking about different magnitudes of discharge, some that are large enough to create some broad scabland terrain, others that are smaller to create eschers. How do we produce all this? Well, we're gonna have a bit of a look at how and where we produce meltwater in glacial systems and where we can store it. And we've got really two major options. One is storage, well, production first and storage at the surface of a glacier from surface melting on a seasonal basis. Some of that water can be stored temporarily. When I say temporarily, it's usually a few seasons. The pressure of the water that accumulates on the surface tends to wedge the ice apart so that the water at the surface makes its way to the bed and connects to the bed and where it can drain. So the ability to store lots of water on top of the ice, that's a difficult proposition, but it's perfectly fine and perfectly viable as an option to produce water that might create eschers. Our second option is to also recognize that we can store a fair amount of water underneath a glacier. We can store water in topographic depressions, but we can also store water in smaller areas just created by basically the pressure distribution at the bed of the glacier where we can pool water. And in this case, we might be able to pond larger quantities of water that might lead to larger discharge. Here's an example just for a visual. Over a few years in Greenland, the production and the growth of surface melting that leads to little ponds. And those little ponds you'll see on the rest of the cross section here, those surface ponds can propagate through the ice to connect to the bed and ultimately drain out the front or lead to a pool of subglacial water. So this is an observed phenomena in modern ice sheets. It's accelerating just given the global climate, but it's entirely reasonable to imagine that at least at the very least, the surface melting would be occurring for the Okanagan Lobe during its retreat. If we want to store more water, if we want to think about the potential for storing large amounts of water at the bed, we have to look at the areas that might be affected. And so the next few pictures are really focused on the major valley system that connects to Waterville Plateau. So again, for reference, this is Okanagan Lobe. Waterville Plateau is here. Omak Plateau is this triangular portion here. And we're going to look at examples of some of the landforms that are in the Okanagan Valley. And I'm just going to use Okanagan internationally, up and down across the Canadian and US border, because the story is really one that spans the entirety of this long, this is a 200 or 300 kilometer long valley that drains the southern interior of British Columbia and connects directly to the Columbia River. The Cordilleran Ice Sheet, unlike other ice sheets like the Laurentide, is unique in part because it grew and developed on top of very pronounced topography in the Cordillera. Major valleys like Okanagan separated by major summits, and there's a series of these north-south trending valleys. It's a place that naturally tends to trap water. There are lakes today, without an ice sheet on top, there are major lake systems in these big valleys. And for the same reasons that we have water stored today in those major valleys, the same phenomena would have happened during glaciation. The modeling at very large scale shows us that, the tendency to pool water in parts of the Cordillera. Even if we look at other examples from, this is the Okanagan here with a big bend around the city of Kelowna, if you're familiar with that, the geography of that area. Basically, Okanagan Valley is a natural trap to store water underneath a glacier. So this is a modeling exercise that incorporates the pressure conditions of a cover of ice from the ice sheet and where water naturally tends to migrate and pool underneath the ice sheet in Okanagan Valley. If we want to build a bit of think of it as a reservoir of water underneath the ice sheet, we can enhance this because in the valley there's a long history of volcanism, including some Eocene volcanism. It's resulted in very anomalously high geothermal heat fluxes over the last 40 million years. And so imagine putting an ice sheet over this whole landscape in an area where there's a natural tendency to have basically a high flux of heat at the bed of the glacier. It simply enhances this production of water and the likelihood of pooling and ponding and storing large amounts of water. We mentioned that the tunnel channels, this idea of channels that can overcome topography is really critical and diagnostic of flows that are driven underneath the glacier. Well, in Okanagan Valley, we see exactly the same types of landform. So the inference of a large area of water storage is reinforced by this evidence here of major channels that be produced during the drainage of such a reservoir of water. So what matters for us is this idea of the longitudinal profile, so the mapping and the plotting of elevation along the length of these two channels, and you'll notice that they go uphill. That's the diagnostic criteria that says pressurized subglacial water flow. It goes uphill again, and they can have long downhill segments, which is fine, but the moment we see evidence of overcoming adverse gradients, that becomes very diagnostic. That particular image is on the north side of the border. If we move to below the border here, we're back to the Omak Plateau, but even the plateau itself is flanked by bedrock channels that exhibit these segments of these reaches of adverse slopes that need to be overcome by a pressurized subglacial flow. And all this leads us, as we're moving southward from Canada to across the border into northern Washington, leads us right back to where we started, leads us right back to the channel network on Omak Plateau, the flanking tunnel channels, and this anastomose network of tunnel channels. So if all roads lead to Rome, all tunnel channels in the Okanagan lead to Moses Coulee, basically. So we're invoking this network, we're invoking this mechanism to produce, deliver, and show us the evidence of this delivery in terms of the channels that have been eroded into Moses Coulee. How much water exactly does that consist of? So this is a busy table, and we'll just cut to the chase. So just pay attention to the numbers that are anything right of those red lines. So what Joel and I have done is we've made some estimates on the discharge, the volume of water that can be conveyed through the channel network. There's a lot of unknowns about this. In part, we have an unknown about, or unsure of the percentage of the network that operates. Is it all operating simultaneously? When I show you this map, are you picturing a scenario where every single channel is full of water at the same time? That would be 100% operation. Or is half the network operating, or 3/4, or 1/4 of it? We don't know. And there are probably some subtle landform relationships that we haven't quite teased out yet. So we're using a range of percentage of the network that's operating. We're using velocities here. A range of velocities are reasonable for documented and modeled velocities for subglacial flow. And from that, we are using the cross-sectional areas. There's a cumulative cross-sectional area for the channels themselves. And with those variables of velocity and cross-sectional area, we can compute a discharge. So the numbers that matter for us, just to put things in perspective, is anything above 1, because 1 represents a mega flood. 1 represents 10 to the 6 or 1 million cubic meters per second discharge. That's the threshold that everybody agrees on is how we define a mega flood flow. So anything 1 or above generates a mega flood through the channel network. It's the volume that corresponds to that. And so you'll see that depending on configuration and the number of parameters and how we organize the parameters, in many cases, we can generate a mega flood or in some cases, well, in excess of that initial 1 times 10 to the 6 cubic meters per second. So in a nutshell, how much water do we convey through this? Lots, plenty. Plenty, when I say plenty, it's on par with the estimates from other hydraulic models. There's been lots of hydraulic modeling done in Moses Coulee to say how much can that coulee actually convey? What's the volume of water? Our numbers are in the range of what's been modeled, and there's both approaches have lots of uncertainties, but it's in the ballpark. And let's leave it at that for now. So if we now think of Moses Coulee as really a coulee produced by subglacial water, how does that now fit into that broader picture of the channel scabline? So one consequence of that work is that Moses Coulee either doesn't at all or doesn't have to convey water from glacial Lake Missoula. Its formation, its operation during the period of Missoula flooding can be absolutely independent of any drainages that happen from Lake Missoula. Does it guarantee that it gets no water from Lake Missoula? No, not entirely. There's still some possibilities for some water making its way into it, but it becomes increasingly difficult. And I'd argue that the network that's mapped here, this anastomose network on Waterville, offers a much better and simpler routing system to get water into Moses Coulee. We are without much trouble, into mega flood range discharges. In other words, we are capable, and we will likely, this is probably an understatement, we are almost definitely producing landforms and leaving behind sedimentary records that are near identical or capable of being similar to those from drainage of Lake Missoula. In other words, there's a potential that now we've got 2 different areas involving very large quantities of water and delivering very large quantities of water onto that landscape that produce very similar records, both sedimentary and landforms. And how do we disentangle those two? How do we recognize what's a contribution from subglacial water versus those from proglacial lakes like Missoula that are draining? And the last consequence of this and the realization is that I showed you an example just now of drainage towards Moses Coulee via a subglacial network. That is not the only evidence for what I would call northern sources of meltwater affecting that landscape. And when I say northern sources, I mean non-Missoula sources for water. And that I'm going to dive into that in the next 10, 15 minutes. Have you been to West Bar? Have you seen this giant? Yes. I mean, if you ever stare at that landform, that giant bar, this is probably the most diagnostic landform of megafloods. You cannot produce giant bed forms on this scale, like West Bar, in any other setting than megafloods. So if we recognize very large bed form systems, it's almost a direct association with megafloods.
Where is it?
This is outside of Quincy
Thank you.
on the Columbia. Bed forms like of that scale, so giant, what people call giant current ripples, even though they're not really ripples, but let's go with that term. They're abundant throughout the channel scabland. So the brown areas are roughly corresponding to the areas inundated by floods from glacial Lake Missoula. It's your traditional thinking about the configuration of the channel scabland. Telford's Crab Creek, it's Petey Palouse, and Drain Coulee. The black squares are places where giant bed forms have been documented. Vic Baker documented over 100 sites in the channel scablands where these occur. What I'm going to do next is show you some examples of giant bed forms and other indicators that occur not in the channel scablands, but that occur on the margin or clearly underneath the footprint of the Cordilleran Ice Sheet. So the orange dots, the yellow dots, and I won't talk too much about the red ones, but this is really the distribution of large bed forms beyond the traditional sort of area of the channel scabland. We're also going to look at another potential indicator of outburst floods, what we call ice block scourers. This is a picture from Iceland from 1996. In 1996, the most recent, one of the most recent Jökulhlaups or outburst floods occurred on a sander. This picture was taken in 2003. And what is striking about that surface is that there are these little depressions. In this case, some of them have lakes. And those depressions, during the outburst in 1996, had a block of ice that was stuck in the sediment of the outwash plain. And the block of ice has since melted, but during the flood, the block of ice was stuck in the sediment and flow had to divert around the obstacle. And it scours and erodes, and it produces these really recognizable longitudinal and linear scours around the block. It's exactly the same pattern that you have when you have flow around the pier of a bridge, for example, or if you've ever been on a beach and you have a little pebble that's in the sand and you see a little bit of scouring around the pebble. It sets up what we call a horseshoe vortex. So this is what you should envisage. There's a block of ice shortly after the flood. The flow of water excavates a trough in front of it, and the trough extends laterally downflow to produce these, let's call them wings or something along those lines. Those indicators are really important because if we can recognize these types of features, if we can recognize very large bed forms, they become proxies, they're clues to the occurrence of a large outburst. So I'll first give you a quick overview. This is entirely the result of the availability of LiDAR. This is opening entirely new, literally eyes and perspectives on some of the landforms. But I'm going to show you a quick overview of some of the bed forms we've been able to identify over the last few years. And then I'll show you how we use these bed forms and also these scour holes to say something about the magnitude of the flows that create them. That's ultimately where we want to go. So this one is near Omak. So in Okanagan Valley again, on the US side of the Okanagan, on a terrace near Omak. Notice the scale here. There's a scale bar over here. So we're looking at a field of bed forms that's nearly 1 kilometer long. Another one in the same area, highlighted in yellow, near Omak Lake, so a little bit to the east of the previous example. One on the Canadian side of the Okanagan this time. Again, the scale for you. So you're looking at something that's almost 1 kilometer long. We're looking at spacing often that is in the tens of meters between the ridges of these features, and often amplitude, so height from the top to the bottom of the top of the crest to the trough, and then usually in 5 to 7 meters in terms of amplitude. These are enormous bed forms. They're morphologically very similar to what you might see in a river channel in terms of small ripples, but they are orders of magnitude bigger than what you would see in a channel because the flows that create them are also orders of magnitude bigger. A few more examples. These are just north of Spokane, really spectacular, much bigger than the previous ones. This is a field. In fact, it's 2 fields. So this one and this one that are connected. So I've blown up the areas, but you can see the morphology really well. And the next one that's a bit further to the south of that one, but they're connected across the area. They're associated in this case with a cataract that probably receded. So a fairly, not just voluminous, but high velocity flow that produces this field of bed forms. The whole extent of it is over 6 kilometers. In terms of the size of the field. And one that's just notable because of its strange shape, but very much an arcuate system, so kind of curved, an unusual pattern that we don't typically see, probably related to the configuration of the valley. And it's flowing from the right to the left, coming down a valley. You can see there's an area of intense bedrock scouring and then expansion of the flow to produce these bed forms. So they're notable because we can now see them. Some of these features were not all mapped. It's really LiDAR that's allowing us to see them. Similarly, some of these features, like these scour holes, were not always visible, but LiDAR helps us identify them in the landscape. So I'll come back to this image for a second, just to give you a perspective on the size of these holes that you have in Iceland. So some of these larger depressions are on that scale. There's a couple of people standing by the rim of one of these blocks. So picture in your mind that at the time of the flood in Iceland, there's a big block of ice occupying that space, and the flow is moving around the block itself. It's not sufficiently energetic to lift it out of the hole and roll it around, but the flow is diverting around. And if we go and look at some prominent terrace surfaces, and these are terraces produced during the deglaciation of the Cordilleran Ice Sheet, during the retreat of the ice sheet. This will be a major difference between what we talked about for Moses Coulee, that was subglacial and closely associated with the maximal extent of the ice sheet. This is during deglaciation, as the ice sheet is melting back, producing lots of water. Some of the tributary valleys of the main stem Okanagan, this in particular case, it's called Horse Spring Coulee, we can start to identify on those terrace surfaces some similar scour holes as we just saw in Iceland. So you can see examples here of that very clear kind of horseshoe depression with the lateral extent of the scouring from a central point near the top. And so these have just been outlined for you a bit. If you're on the ground, these are very subtle features, and I'll point them out to you. There's a couple of pickup trucks for scale. That's me with the red arrow over here, the thing that looks like a pair of legs. That's me. And here's a scour. Here's the front of a scour. Here's the residual ridge produced by that. And the front of the scour leads to lateral furrows this way. There's one here. There's one here. I'm standing on the edge of one. There's the scour. There's the lateral ridges. There's the residual ridge. And so subtle features, but we can identify them. And of course, what I'm hoping you can picture is that at the time of water flooding the surface, we've got something like this happening. We've got blocks of ice occupying the depression, and we've got, it's obviously all covered in water. I'm just showing you the turbulent structure that produces the scour, but it's the block that is creating the blockage that induces the turbulent structure that produces the scour. The key for us is how can we, but it's a bit of a rhetorical question, yes we can, how can we use these landforms like these scours and the big bed forms to say something about the magnitude of the floods that produce, the flows that produce these forms? So one option for the scours, and this is the LiDAR version of what we were just looking at. So the scours that we were just looking at are here, here, I was standing by this one, there's another one over here, you can see they're really all over the surface here. These are not unique to that particular part of the world. We saw them in Iceland, but they're also in many other places where there's been mega floods and there's some kind of obstacle, whether it's ice or a big boulder that is in the flow, it induces the same scour. And so there are some simplified formulas that allow us to calculate the velocities of the flow that are necessary to produce scours of given morphology. In other words, there's a relationship between the size, the width of a scour, the residual ridge, the depth of the scour, all those parameters are related to the intensity and the velocity in the flow. And so to make a long story short, the scours on that surface basically tell us that the flows are moving at somewhere between 3.2 to 4.4 meters per second. We can go through a similar exercise when it comes to the bed forms, the large fields of bed form that we identify on all these deglacial terraces. And what I've done is I've just plotted in color, just to symbolize the different locations. I've plotted these on the same diagrams that Vic Baker used in the 70s when he did the hydraulic reconstructions of the large bedform fields in the Channel Scablands. So the 100 set of documented bed forms, we're using the same diagrams, and I'm just overlaying the data, or the morphologic parameters, and in this case, it's what we call the ripple chord length. And the chord length is really just the spacing between the ridges of the large bed form. So the spacing of the bed form is intimately related to the flow conditions, the velocity of the flow and the depth of the flow. So the first thing to notice, some of the bed forms we identify plot in the same range as those that are in the Channel Scablands. Some are a little bit lower down here. And we can make an inference from the ripple chord length or the bed form chord length as to the velocity that's required to produce that particular morphologic set of conditions. And so in this case, in terms of velocity, we're looking at flows that are on average somewhere between 6.5 to 10 meters per second. So they're faster than those that produce the ice blocks. And on the extreme end, we're creeping into 15 to 16 meters per second. These are extremely fast subaerial flows. Remember, these are not subglacial in this case. They're in front of the ice and they're just exiting some form of, they may be exiting the ice, they may be exiting a ponded water body, but they're basically produced by subaerial draining. Same diagrams also allow us to relate bed form morphology, the chord length to the flow depth, and the patterns are the same, and the story is very similar. We plot in the same fields, maybe a bit lower in some cases, but the inferred flow depths on the order of anywhere between 13 to 17 meters, and in some cases as high as 65 meters of water, where we produce these very large bed form trains. Let's bring all that together, because if we've got information on flow velocities and we have a bit of an understanding of the landscape, what we'd like to do is be able to calculate a discharge. The calculated discharge, that's the volume of water that is released when we produce these different landforms. to arrive at discharge, we need some measure of the width of the flow, some idea of the depth, and some idea of the velocity. Well, the last two variables we've just dealt with. We've got depth, we can infer depth, and we can infer velocity using the Vic-Baker diagrams. The flow width is the unknown, and to do that, we need to really consider the conditions in the landscape. So I'll just show you an example of how we use that kind of information. This is the bed form field that I first showed you. This is the one near OMAC. And in the most conservative representation of that field, the width of the flow that creates this field is about 700 meters wide. But when we have a bed form field, whether it's enormous like these or in a river, the flow is almost never restricted to the exact width of the bed forms. It's bigger than the bed form. It's wider than the bed form. So how wide was it? Well, was it as wide as the surface that we find them on? Well, perhaps. So that would raise it to 1,200 meters in terms of the width of the flow. But this is an erosional scarp of a terrace, which suggests that the river, the modern Okanagan River, is in size and eroded some of the formerly more extensive surface. And so how wide was it? Was it as wide as the valley is wide? Well, perhaps. And if that's the case, now our flow width is over 2 kilometers. So we're perpetually dealing with estimates based on ranges, much like we did for the Moses Coulee and the subglacial drainage system. But nonetheless, it allows us to arrive at an estimate of discharge. So if we bring all that together, what we're seeing now is that combining bed forms and combining ice block scours, we're able to estimate discharge. And we're creeping into the 10 to the 4, 10 to the 5 on the very high range if we're using the upper ranges of both the velocity and the width of the flows. We're actually creeping into mega flood scale discharge, 10 to the 6 and a bit beyond 10 to the 6. The ice block scours tell a story of lower magnitude flows, but not radically lower magnitude. So 10 to the 4 to up to 10 to the, some cases 10 to the 3. To put things into perspective, that 1996 outburst in Iceland that I keep using as an example, that was a discharge of 5 times 10 to the 4. And that was a major, major geomorphic event. It reorganized that outwash plain to the ocean, and it deposited almost 10 meters of sediment in 2 days over an area of 500 square kilometers. These are not trivial flows, even at 10 to the 4. It's just that, you know, the scablands are just that ginormous. Like the magnitude of the flows, 10 to the 6, or beyond that in some cases, it's just unfathomable how energetic and how big that is. But 10 to the 4 seems like almost like a disappointment. But in reality, it's a major, major geomorphic event if you have any flow of that magnitude. So where do these floods come from? Where do these ice block scours come from? Where do these large bed form trains come from? In some cases we know, in some cases we don't. In most cases we don't know, but there's a couple of good sort of connections between potential sources of water and associated with a bed form train. One that I showed you from Okanagan Valley most likely comes as a result of the drainage of this late glacial lake that's called Glacial Lake Penticton. If you've ever been to the Okanagan Valley in Canada, this is the city of Kelowna, Vernon, Penticton down here. And at the close of the last ice age, there's a lake that occupies the valley. There's a lake there today, Lake Okanagan, but it's a bigger lake. It's a higher lake. And it's a higher lake because there's a plug of ice that holds it back. And when that plug of ice lets go, the lake drains, and you'll see that the blue surface, which marks the high stage of Lake Penticton, drops to the modern stage of Okanagan Lake. And in the process, we drain somewhere between 75 to 125 cubic kilometers of water. And in the process, we also probably generate this bed form train that I showed you earlier, because that bed form train occurs right here at the outlet of the lake. So this is one of the bed form trains that yields the highest discharge magnitude, so 10 to the 5 and above in our little estimates, and it's most closely or most confidently associated with probably this drainage of Lake Penticton. For others, not clear really what the sources are, but there's an ice sheet decaying, and so the reasonable extension here is that the ice sheet is generating these by releasing water during decay. So I'll conclude on some of these basic ideas that I've presented tonight. There's an enigma around Moses Coulee, and I think we would argue, Joel and I, that really it's not that much of an enigma. It's only an enigma if you are looking for essentially the wrong drainage pattern. So if you are expecting to see, and if you're expecting to see connectivity to the known scabland drainage routes, then it will always remain an enigma. If you expand your thinking to other configurations of drainage, and in this case, configurations like this anastomose subglacial network, it delivers literally and figuratively an answer to the water getting into Moses Coulee far more easily than with any other configuration and drainage system. So the enigma, would argue, isn't really that much of an enigma. There's a very complex and very long-lived history of water drainage from sources other than Lake Missoula. It doesn't mean that we're replacing glacial Lake Missoula entirely. It's not instead of Missoula, it's in addition to water from glacial Lake Missoula, because now we're seeing evidence of subglacial drainage, but also during decay, proglacial drainage, very much focused along the north-south trending valleys that all lead to the Columbia River. This is my next important point, is that these subglacial and proglacial floods drain to the Columbia Valley. And that means that they overlap in space with the Missoula flood routes. So I said, this is not a proposal to replace Missoula as a source for the channel scabland. It's in addition to, and the complexity arises when we realize that both water sources, or all three water sources, or the multiple water sources, drain to the same areas. In other words, there are multiple events that may overprint each other, but occupy and utilize the same drainage route, the Columbia Valley being the main one. And that means that it has the potential, and it should really make us think in the future about how we interpret features like giant bars along the Columbia River. The West Bar, for example, there's others at Pangbourne, and there's a big bar at Pateros, and many other features that are in the channel scablands, and the origin of features like the Tushy beds. Are they all necessarily a product of Missoula floods? Well, I would argue that they're not necessarily. And we really need to start thinking more broadly about these alternative and additional water sources to try to untangle some of those big questions. Because it's not, there's still, let's just leave it at, there's still very many open questions about the timing of drainage. And now we've got to consider an expanded array of sources for not water. Thank you. I'll leave it there so we have some questions. Questions, comments, or yes.
Could you talk about the bridging of the ice over the channels underneath the glacier?
The bridging.
There's a hollow effect underneath the glacier.
So when we have a
The
subglacial
glacier-
drainage,
The glacier, yes,
Yes.
the glacier is, 2.5 kilometers high. Hey,
maybe, yeah, might be a little thinner, but yeah.
why, in your studies, have you come up with an explanation for why it didn't just crush itself down into those channels?
It does after the channel is empty of water. It will reoccupy the channel after. But at the moment of drainage, there's enough pressure to basically, it does two things. It reduces what we call the effective pressure, which is the weight of the ice countered by the pressure of the water. And so essentially the glacier kind of detaches itself from being anchored on the bedrock. The other thing that the water does, it actually erodes upward into the ice as well. So it's going to expand to some unknown amount upward into the ice. And we're going to accommodate the discharge. But after the event is done, the ice will creep close. If it's thick enough, it'll deform and creep back into the channel to reoccupy the channel. And that might be where we start building an esker, for example, when we return to a drainage system that's not quite as energetic as that previous one. I had that, I think. I'll just show you that subtlety. I think it's in my diagram. So you've got the lobe during the subglacial flood. It produces the channel, but now you notice that the ice now occupies the channel that it previously carved for itself with the water
I
cover.
didn't think of it.
Yeah, and then we've got the esker.
Well, does it destabilize the ice above it? Is that at some point?
Yeah, there's all
Because it's-
kinds.
No,
Yeah.
not possible.
Yeah, there's all kinds of potential things that happen when you have that much water, even if you have portions of the network occupied by water or conveying water. There's an almost instantaneous loss of friction wherever you lift the ice. And the question is often, well, you see a channel, but how do you know that the channel didn't actually initially start even broader? And there is in fact evidence for some of that. I'll show you on this area here. We see, for example, that even though we can clearly define the boxy channel shape, the areas on the margins are actually scoured of sediment. So it tells you that the water initially was broader than what the resulting channel ended up looking like. It was at least as wide as where you've scoured the sediment off the bedrock, because that's all basalt. But beyond that margin, you leave the till. So we erode and we strip away the till, but at the same time, the flow is focusing into what will become a channel. So when you do that, the ice loses friction. So it thins, it can accelerate, it can do all kinds of interesting things at the same time.
So what kind of water pressures are we talking about?
That's a good question. In terms of a number, I'm gonna give you an unsatisfactory answer, a lot. It's enough to lift an ice sheet in some places, enough to generate. I can't remember. Joel, do you remember? Do you have a number in mind?
Well, I can relate to the water pressure in our house.
It's thousands of times, probably.
I don't know the number.
Yes, I can't remember the
It's the
number.
density of the ice. It's the weight of the ice.
Nice,
It's at the same pressure, more close to the
so
weight of the ice.
rho GH,
Very
so density, gravity, and thickness.
good. Row is 0.9.
0.9 times 9.8 times some unknown thickness. There was one up here, then
But I was, it seemed like you hesitated toward the end. Is it theory that you would say that your conclusions, or would you say it's fact? Or what proportion?
is there a middle? Can I pick something in the middle?
Well, someplace, but
I think it's more than theoretical, but it's certainly not, I mean, I never claim it's fact. I think there's enough evidence, there's enough smoke that there's a fire about this somewhere. So it's more than just theoretical suppositions, because we've got some pretty convincing field evidence. The bed forms are one, there's a very good quantitative basis to relate the shape to the hydraulic parameters like the velocity and the depth. Similarly with the scours. So those are more than just suppositions. I think when, it's really the field evidence that's driving the thinking to arrive at some kind of discharge calculations. There's a ton of unknowns, of course, and there are a number of assumptions we make about with the flows and relationship between landforms, but
well, you make a good case.
I think it's
appreciate
more
that.
than just sort of fanciful notions. Yes,
We don't have coolies around here, but do we have other evidences here in the King County area?
yeah,
Of the type of-
you don't have coulis because you don't really have basalt.
Right.
So you're not gonna get the same morphology. There's an unmistakable connection there between jointed columnar basalt of the Columbia River basalt and the coulis shape. But you have, I would argue, analogous features that I was showing you on the image. Where is it? The tunnel channel, I'm going backwards, sorry. Sorry, I'm just gonna go straight to the feature I'm thinking about. The map of Puget Sound. Where did you go, map of Puget Sound? I went right by it. Oh, there it is. Thank you. So these, many of these are probably analogous. They're tunnel channels. And they're analogous to the coulis. They just have different shape. And they're not always cut in bedrock. They're mostly cut in sediment in the Puget Sound. But in terms of when they form, how they form, very similar to what
In the direction.
the direction is driven by the pressure gradients, but yeah, generally speaking, there's thicker ice to the north and there's a margin to the south, and so yeah, we got this north-south arrangement, but yeah, from that standpoint, they're pretty much similar features.
I see some questions in the chat.
Oh, okay, thank you.
So we do that question.
I'd like to do some chat questions. Other questions? Are there more mapping projects planned to expand upon this? Yes, there are. They're kind of ongoing.
Your mapping or somebody else?
It's largely ours. It's just project that, we've been, Sky and Joel and I have been working on. So, I don't know how many other people are really working on these questions right now. I don't know if there are many at this point, especially related to the large bed form fields and the scours around the former obstacle of the ice blocks. Any other questions? No, I think that's it for the chat so far. Put aside. Yeah,
You showed diagrams or actually somebody's drawing of an esker. Do you have any photos? Where could I go look at an esker or see it? And the scale, I'm trying to get the scale of it.
yeah, okay, yes. So those are my little cartoons of an esker, but you'd
Right.
like to see the real deal. I understand that, okay. Let's go see, there is one of these pictures that has, is this one? Yes. There's an esker right here on this DM. Right here.
Okay.
That's an esker. So extent, often hundreds of meters, if not a few kilometers in length, continuous or slightly discontinuous. The height, often in the order of 5 to upwards of, the biggest ones are probably about 20 meters, and you have a hair over that. The width is about the same. You want to see some really good ones? Google Earth, and you punch in Sims Corner. Sims Corner takes you to the Waterville Plateau, and there's a stunning example of an esker system right around that intersection of the two roads at Sims Corner. You can see some of it, yeah. Yeah,
I can add to that, there's a large esker down east of the town of Rainier. If you look at our LiDAR mapping in that area,
yeah,
it jumps right out at you.
Okay.
It's about, I'd say 20 feet high, something like that, it's quite large.
Thank you.
they're made of sand and gravel commonly, just
So
because
they
that's what
probably
the water's reworking from the
erode
till. Yeah,
So,
yeah, it's basically, the water's flowing and sourcing right from the sediment that's on the floor of the glacier bed, which is till, so it kind of flushes out the silt clay, and it concentrates the sand and the gravel into this ridge that fills the conduit, that's the half circle conduit. Yes.
Yeah, when you were showing the pictures in Iceland of the sort of alluvial
Yeah,
plain with, a lot of little holes with the lakes and that. Reminds me of the kettles, just west of Coupeville.
yeah. They essentially are kettles.
Yeah,
They are kettles. The only difference is that they are kettles that were caught in a large flood. So kettles, if you're not familiar, kettles are depressions that we find usually in outwash surfaces. And so in the sediment, the sand and gravel that's moved by meltwater, we can transport ice blocks, we can partially or fully bury them. And then in the years that follow, they melt. And so the space that they occupied leads to a depression. So you have this often irregular depression. These are just like kettles. They just happen to be kettles that were replaced by a large flood. And therefore were also affecting the erosion pattern around them because they were in the flood. But if they were not in the flood, they would have just been probably, well, we'd have fewer of them for starters, because those big blocks are rolling on the outwash plain as they're entrained into the flood, and they ultimately come to rest often because they kind of get buried partially and stabilized by sediment. And then that's
if you look at LiDAR
yeah,
around the Coupeville area, it really looks like there was some big flood that washed, from the east to
Yeah.
west right across the island.
it wouldn't be that surprising because we're in a very similar system. We were just looking at the Puget Sound LiDAR with the big valleys. It speaks to similar processes, so it wouldn't be surprising to find similar features. Yeah, this is probably one of those landforms that hasn't been noticed much, but if we start looking for them, we'll find more. That's exactly what happened as we started looking at LiDAR in these areas. We found a lot in Okanagan. There's a few other spots I didn't show you, but they're not isolated features.
There doesn't seem to be much to read about floods ripping across Whidbey Island,
No, there's not much written about that. No.
but it looks like
Maybe, but the notion of floods, I mean, you have to sort of take that with a bit of a grain of salt, because floods can be a variable magnitude. And when we're dealing with the hydrology of a glacial system, we can potentially deal with magnitudes of flows that are much larger than the normal riverine flows, but are still within the range of something not necessarily extraordinary for a glacial system. That ability in a glacier to store water and release it pretty rapidly allows us to have high discharge events without those events being extraordinary in terms of their magnitude. Yeah,
You said the yoga was in, I think it was Greenland,
Iceland,
Iceland was a 10 to the 4.
10 to the
And
4.
some of your calculations were up to 10 to the 6.
Yeah,
What would a glacial Lake Missoula have been? In that
depends where you measure it.
Yeah.
But so right when Glacial Lake Missoula goes past the ice dam and basically flows over what we call the Rathdrum Prairie, so right at Spokane. I think the last number I saw was something like 15 times 10 to the 6.
Oh.
So 1.5 times 10 to the 7. But that's, you know, right out, literally out of the gate.
Right.
And where the water is moving through the fastest. In Moses Coulee, I think some of the numbers are in the 2 to 4 times 10 to the 6. Some of the estimates, Grand Coulee is in the same range, you know, so 10 to the 6. Yeah, so the Lake Missoula, the quantity of water is so enormous out of Missoula that the discharges are correspondingly really, really high. Yeah.
Is that the upper Moses Coulee, is that crystalline rock exposed there, or you just get it well off?
No, it's all basalt. All basalt in upper Moses Coulee. Yeah. The crystalline rocks really start to appear. There's a little bit of crystalline rocks that appear at the head of Grand Coulee. Just a few knobs locally. And then there are a few knobs of crystalline rocks almost at river level in the Columbia Valley. So off the plateau, basically at the modern reservoir level. Otherwise, you encounter them again at high elevations on Omak Plateau. When you're really on the edge of the basalt there. You had a question.
I have heard it stated that, Moses Coulee was carved by ice, not water. The argument being that it has a rectangular section instead of a V-shaped section like you might expect from water.
Mhm.
That argument kind of surprised me when I heard that.
Yeah, surprises me too. So by the same logic, is Grand Coulee carved by ice? No. So I think being a little facetious, but I think the basalt, the jointing in the basalt is such a strong control on the resulting morphology that we end up with boxy cross section. But the other variable to think about is the fact that most likely when those floods happen, they're almost bankful floods. In other words, the entire cross section is full of water. So it's a channel, not a valley. Does that make sense? So it's, however, wherever we want to position, you know, the amount of erosion that happens over time, the cross section is almost full of water. It's not just like we focus flow in a small channel within a much broader valley, which might lead to more of this V-shape. We see hints of that in some parts of the coulee from subsequent smaller magnitude flows, but ultimately we need to carve out this big boxy channel. And that probably means when we look at the modeling of flows through there, the whole cross section is full of water. So that's why I'm saying it's a channel, not a valley. Yeah.
So how did you guys come on this idea in the first place?
Oh, yeah. Well, Joel did his entire PhD thesis on Moses Coulee. And he finished that a year and a bit ago. A year, something like that, year and a bit. And then, and so he started mapping on Waterville. I did my PhD thesis many years before in the Okanagan Valley, north of the border and south of the border, with a bit of work on OMAC. And so at some point we got together and we compared what we've been doing, and there was this convergence.
You know, there was a kernel of an idea.
Yeah, the kernel of the idea. Well, if you want to take it all the way back, the kernel of the idea is back to Brett's almost. It was back to some of these early ideas, and that confounding sort of observation that Moses Coulee doesn't connect properly to a water source. That just always required some explanation.
Sitting down to write my thesis, and I was saying there are no channels that connect Moses Coulee to the Columbia River. That's a strong statement.
Yeah.
Look, so I started drawing the channels, and that's what led to the map. that
Yeah.
I showed you. Looking at images like you have on the screen, you can see the channels. Just trace the edges of them, but that took months, delayed the process of finishing, but then I could say there are channels that connect
Yeah.
Moses Coulee to the Columbia River.
They're just,
These patterns that you're-
yeah. They're just a different type of channel. But, yeah. There's a question, is there a possibility of any tunnel channels in the area of the Purcell Lobe? Yeah, that's an online question. Yeah, probably. I haven't sort of specifically looked, but there's a good chance. I mean, most glacial systems or big ice sheets have tunnel channels. It's a matter of just recognizing the morphology. And in the Cordillera, it probably is, you know, a major structural valley like Okanagan or the Purcell Trench or the Rocky Mountain Trench may well act or play the same roles as a tunnel channel in terms of conveying subglacial water. So what they look like might vary, but as a concept or as a possibility, that's more than reasonable. In fact, I would argue it's probably expected that there's some elsewhere in the other valleys. Yes.
Whatever process created Moses Coulee, does it show evidence of being episodic with each of the ice ages?
Ooh, that's a good question. I think it's reasonable to think that the whole coulee wasn't carved in one glacial period. How many? That's less clear. Was there an antecedent river system? That's also a high probability, I think. How far back in time do we have to go to think about what the river, the ancestral Moses River would have looked like? And how many glacial cycles has it taken? Don't know. Really, I don't know. We've wrestled and discussed this a million times about those possibilities. It's extremely difficult to tease that out, particularly in a landscape that's mostly erosional. If there were deposits, and there are some deposits that might yield some information about which parts are eroded and when, and that's sort of something that Joel has worked on in his thesis in part. But when you're fundamentally dealing with areas of erosion, it's kind of like wiping the slate clean every time and leaves no record of what happened before. And if we don't have remnants of what was going on before, it's a guess, basically. But it's a bit more than just a wild guess. It's reasonable to think that there would be a fairly lengthy evolution of that system. Yeah.
I was curious, why did the Puget Lobe travel so much farther south than the rest of the glacier? Just deeper or?
Yeah, it's the Puget Lobe, as far as we can tell and what we understand, and the channels in the Puget Lobe speak to this, is a very wet-based glacier. So it's got a lot of water at the interface. It's not always completely anchored and grounded to the bed. It's kind of like it's periodically lifted, or the pressure is greatly reduced by by widespread high water pressure underneath the lobe, which means that it can sort of the slip and slide game, you know, that kids run and slide on. So it's the same kind of idea. It reduces the friction, and the ice can extend quite far. It'll thin, but as it extends, but it'll it can travel quite far, quite south in this case. And then when it retreats, because we're in an area where as ice is melting globally at the end of the glacial period, sea level is rising, there's encroachment of seawater that also enters into the equation and lifts the glacier. So the retreat is also fairly rapid. So the lobe advances pretty quickly to a fairly southern position, but also retreats fairly rapidly because it's a very wet environment for a glacier. Yeah.
Also on the ice source areas, that's where I don't come up all and get it used to get check in the back. Deep bed.
Yeah. The Puget Lobe, if you take it north of the border, is in the Strait of Georgia. And it enters into an existing depression that's marine as it advances. And so it's almost from the start, it's going to be on a fairly wet environment. Even though the sea level drops, we're still in this setting where there's a natural trough that's got lots of water. Yeah.
Did the Puget Lobe also benefit from a greater accumulation of snow and ice west of the Rocky Mountains? West of the Cascade Mountains?
Yeah, so the Puget Lobe is largely supplied in ice partly by, I think, Cascade ice draining westward, but the coast mountains of British Columbia draining also westward into the Strait of Georgia. So the onset of glaciation the ice sheet builds north of Puget Sound, and ice will spill westward into the Georgia Depression, the Strait of Georgia. There'll be ice off Vancouver Islands eastward, smaller amounts, but still some ice into the Georgia Depression, flowing eastward, and then they kind of coalesce with ice masses and start moving southward to form the Puget Lobe. So they're very close to the sources of ice in the Coast Mountains. So that there's a fairly rapid and voluminous supply of ice to the Puget Lobe. When you look at lobes east of the Coast Mountains, so southern British Columbia, Okanagan Lobe is, arguably the closest to the source of the Coast Mountains. It's also the biggest, but any other lobe, as you move eastward, gets smaller. It's best that we can map them, because they're probably in the center of British Columbia. They're far removed from the ice sources. You got to build ice in the central and southern British Columbia so that it can start flowing southward. And as you move eastward, you get to the Rockies, and you get another big lobe there, the Flathead Lobe, because it's also directly connected or closely connected to the source in the Rocky Mountains, right? So there's sort of this, think of it as this dry middle or this starved middle in southern British Columbia that limits how big the ice can build and how extensive the lobes can be when you're in central Washington. Does that make sense? In terms of the supply, it's really about the supply of ice. All right. Good.
Thank you.
All right. If you want to read the article, it's open access on the